fjerne den, eller er det noe du bruker?
Ja, det kan du fjerne.
Hvor? Hvor stikker det?
Innpå Uttak til strøm til mobiler og PC sånn under pulten. Under bordet så er det uttak til PC og telefon.
Welcome everyone. We'd like to have your attention, please. So we'd like to welcome you to the first Demystifying Deep Learning and Artificial Intelligence International Workshop. This workshop has been hosted in the Bay Area previously a few times, and we're fortunate to bring it over here to Norway for you. So we're really excited. We have heard that artificial intelligence is really starting to break through in this area, and so we hope to be one of the first people to really drive that forward. So myself, my name is Montoya. I'm the founder of Accel.ai, and basically we are an accelerated career development program to train artificial intelligence engineers. We're starting with a series of workshops, and then from there we're developing a full program that's actually about 7 to 10 months. But you'll get more information on that later on today and tomorrow. And we'd like to introduce as well Olga from Noroff.
Okay. Hi, my name is Olga Alexander Foss. I'm the principal of Noroff. Just like to welcome you to our campus. This is a brand new campus. We moved up here in August. 3,500 square meters. We are a tertiary private educational institution with a very strong focus on we have a digital DNA and a strong focus on technology. I'd like to welcome you. Those who want will get a tour afterwards. Okay.
And Anders from Nordic Impact.
Thank you. Hi, I'm Anders. So I'm one of the co-founders together with Laura and Olga, Accel.ai and Noroff. So we are from Nordic Impact. And we do this because we believe that AI will go mainstream. And we need to humanize AI. We need to have AI to work for the best for the humankind and the planet. We have an ambition to train 10 million people in AI globally. We started in the Bay, we train in Norway now, and we go to Ukraine soon, and then etc. We'll do 3 continents this year. And we will create 10,000 business ideas, and we will establish 1,000 companies in the next years to come. So it's pretty good ambitions. We have to work hard, but I think together we will actually make a wave. This is the first wave in Norway. And we have also Sintef, Itera, and then we have great speakers from different kind of companies which you will enjoy throughout these 2 days. So I just wanted quickly to also just give you, because you said that it was okay, to give us a little bit a snapshot of what Nordic Impact is doing. And Ida, we have a big thing coming up in May, right?
Yes. So one of many things that we do in addition to this event.
Just we're live streaming it, so if we could
Okay,
close to the mic, we'll be able to
Cool.
get it out there.
Okay.
Yeah.
Wow. Scary. No, so I'm also working with Anders and Tyral in Nordic Impact. We do a lot of different things in addition to this AI workshop. So we do something called Catapult Future Fest, which is a tech conference that's going to be at down close with the Opera House, where we focus on exponential technologies, blockchain technology, AI, VR, and impact investments, the money that is directed to these technologies, focusing on solutions that can save the planet. So basically the combination of technology, money, and how can we make the solutions that can be part of solving some of the great challenges in the world. So that is in May, 10 to 11.
Thank you. And one last thing we would like to share with you is that we also, Hakkon, you can come and share it because you drive the initiative.
Sure. Should jump in the middle. So one catapult to the other. So I'm Hakkon Brunel. I'm heading up our new Catapult Accelerator, which is a brand new accelerator. So Nordic Impact is the main investor, and Harald Anders here, Sagar, our CTO, and some of our main partners. Also, we have Sean Percival from 500 Startups. He's part of the core leadership team, and we have ERA in New York, the biggest accelerator in New York, as a key partner. And our accelerator is really sort of in the same kind of spiel here, working with companies that want to do something, make the world a better place, environmental or societal, but in addition, at the same time, make really good business. And we think that this can happen if you use technologies, exponential technologies such as AI in a smart way. We think this is the future, and we're starting up our program now in Oslo. In August, so in September and October this year, first batch, and we have a fantastic lineup of mentors in these different domains that we operate in, including in AI. So Laura is one of our mentors, and it's fantastic to be here and have you over here. And applications are open on catapultimpact.com.
Thank you. All right, thanks.
Yes, thank you. And Isabel, my co-host, will be introducing our first speaker.
Yeah, I'm Isabel, and I work at, I founded a company called Tank, which works on getting more women into technology, and I'll be speaking shortly for you tomorrow about a little bit of future technology, because I graduated from a university called Scikit-learn University, and also the importance of diversity in technology. But I have the honor of introducing our first speaker today, who is called Ingvild Lyckander, and she works at Beck Consulting, and she will be talking about mathematics for artificial intelligence. So Ingvild, come. Thank you.
Hi everyone.
Hey.
Sorry for my English. It's a bit rusty after a couple of years since school, but I hope you will understand me. And we will see if this works. How far can I go to the side? Okay, thank you. Moving around, I usually do. Yes, great. Hi, as you already know now, my name is Ingvild. I'm working there. I really like math. I like it so much that I studied it 5 years in the university, and that's 2.5 years ago, or since I graduated. So I still can't stop talking about math, obviously. And that is why I have this energizing title for today's presentation. So I hope you bear with me, and I hope we will have fun anyways, even though you get me. But since I started in Beck, or the thing is, I graduated, as I said, from applied mathematics and physics in NTNU in Trondheim, and I saw that with my education, I could take a PhD, or I could become a math teacher. and I wouldn't do it either. So I did it was like everybody else did, become an IT consultant. But then, luckily, I found machine learning and data science, which actually is math in disguise. It's I found eigenvectors, I found matrix, I found gradient descent and differential equations, and I was finally on safe ground again. Because there are many, many important principles in machine learning that are heavy, heavy math. Like in calculus, or partial linear algebra, optimization theory, statistic probability theory, among more. But I have a disclaimer. To do machine learning and to apply these methods, you don't actually need to know math. So if you want, you can actually even take coffee for an hour. Of course, if you actually doing the PhD or you're a scientist, and you're actually making these molds, of course you need to know this math, or all of this. You should at least. But if you're like me, you're just applying them, and there's so many libraries. There's so many good like software as a service on machine learning, and to apply them, you don't actually need to understand what's happening in the box. But still, it could be good to know, like, at least some of how it's working, so that you can improve your models. And what can I do to make it better? If it works, it runs, but you want to, of course, you want to improve it. So hopefully, I will give you some tip on how to move on based on the mathematical principles that all the statistics models are built upon. So I try to what is important in what I've learned in 5 years. So what is important to understand from the mathematics to be able to do machine learning. And I ended up with all this. So this is the presentation today. First we will have some statistics. We will move over to linear algebra to see if we could make our problem less complex. We will then look at some optimization theory to see how actually the models or the statistical models are searching for the best solution. And then finally just have some fun with probability theory. And then finally we are finished. So hopefully it just lasts an hour, we will see. If you have any questions, you can try to take it while I'm talking. Otherwise, we can, as I said, I think we have enough to go through. So I will be here the whole night today and tomorrow. And then we can do it in Norwegian. So, but in that, actually, it's really fun. I work with a group of people. We are 20 people working with machine learning, trying to apply that in our daily projects. And I asked them, what kind of mathematics or principles from math did you wish you had known before, or what do you actually are curious about? And they said, it's a bit sad to know that, but you don't need any math, but I read a lot of papers on deep learning and neural networks, which is, yeah, all deep learning actually, and the most forefront in machine learning. And I said, I cannot understand what they're saying because of the notations. It's all Greek. So it stops me. I used to spend a lot of time Google what the notations actually mean. So I will not take like all the notations now, but there will be some notations on the way, and then there will be a little Greek surprise to explain it to us. So we'll see. So don't be afraid. Let's start. Crash course in machine learning. No, sorry, in statistics. It actually would be word bonanza, so bear with me. We start with the mean. I think you all know what the mean is, so the average of a sample of data or a vector. It's, and there already is the Greek guy explaining the sigma sign, the notation of the sigma. Sigma is this Greek letter here. It says that sigma of a vector is just adding all the elements in the vector. And you can either, like you say here, like you see here, specify which elements you actually want to add. You don't have to take the whole thing. So we said from element 2 to 4, which means x2, x3, x4, sum them up, and in this case we get 12. That's all I need know about sigma. So the average of a vector, you sum it up, divide it on the number of elements, and you get the average. Just remember that sometimes we want to use the median instead, since in the average you are kind of influenced by the really strange outliers. Like if there's a really rich guy in town, he would definitely make an influence on the average. He wouldn't change the median, which is the central element in an ordered vector or list. Standard deviation is important in machine learning, which is actually just a measure of how big variation there is in your data set. It's calculated as, here to me, is the average of the vector x. For each element, you find the difference between the element and the average. You square it, you sum it, remember sigma from the Greek guy, take the average, like dividing on the number of elements, and the square root of that. It's not maybe intuitive, but if you look at the probability distribution of it, which maybe is unfamiliar for some one of you, but it just means for the value of 0, what is the probability we get that value? You see that the standard deviation can give you a measure of how much data is within a certain amount or certain distance from the average. So
and that's exactly why it's brilliant to have you here, because you do that. Because when we read the papers, and we're not very good at math, then we never get these. We just get the Greek, and then we get a lot of Greek, and then that means, and then there comes something completely ununderstandable. Whereas this, anybody can understand that, right? So brilliant.
Good, thank you. So in normal distribution, which is this one is a normal distribution, is the best distribution we have. 68% of the data lies within, we say, one standard deviation from the average. Correlation is also very, very important in machine learning, of course, since it's looking on how two variables are related. For example, again, you can ignore all the Greek. Between x and y, what is the correlation? How do they depend on each other? For example, if x is increasing, when x is increasing, if y is increasing, they are positive correlated, and correlation of x and y would be almost 1. If when x is increasing, y is decreasing, the correlation will be close to -1. But when they are just random, so if you know the value of x, you can't say anything about y, the correlation between those two would be about 0. That was a little crash course we need to know for later on. But now let's have a little quiz, since I've already tried out. Let's say that you have a disease. And you have to go to the hospital to get cured from that disease. And you can choose between 2 hospitals, Hospital A or Hospital B. And you know that for Hospital A, all the patients with your disease, 85% of them got cured in Hospital A. While, on the other hand, 7% got cured from the same disease in Hospital B. So which hospital do you want to go to? Who wants to go to A? Good. And B? Yeah, good. A is obviously the best one, so of course you go to A. But then you remember, oh, I know the age of all the patients. So I will see, and of course we are young, so we will see for all the people younger than 50, how many of them got cured at Hospital A and Hospital B? And now the tables are turned. Now B is a much better choice than A. okay, that was good observation. Let's go to hospital B, you say, right? But then you're curious, what about the people older than 50? What is the numbers then? Why? What? B is still the best option. How is that possible? How can B be better both if you're younger than 50 and you're older than 50, even though A is better in total? Yeah.
A lot of people that are 50 years old.
Yeah. Or probably the ratio of people younger than 50 is much higher in hospital A than hospital B. So as you say, see that the probability that you're cured if you're younger than 50 is much higher than if you're older than 50. So if there's a lot of young people in hospital A, they will take up the average. So you got tricked that you think that hospital A is the best, but actually hospital B is it, because you can't just decide your age. Right? So hospital B is the best choice here, and that is funny about statistics, that when we're doing machine learning, we actually have to take a good look in our data. We can't just have a first sight and then just assume a lot of things and work on it. You should spend a lot of time getting to know your data. But that's hard. The last statistic crash course word is the variance, which is actually just standard deviation squared. So it's the same, it's just how the values are, how much variance or how much variations there is in the data. So if you look at this example, green line has a much higher variance than red line, since they are much more spread out along the x-axis. And that variance is used in many ways in machine learning. It's a good way to explore your data. And now we'll see how we do that to measure how good your model is performing. So let's say we have input data, and we always have that, at least in, yeah, unless we're doing like robotics, and still we have input data. We always have input data in machine learning, which is usually you can represent as a matrix. Here each row is an observation. For instance, if you want to model what will the price of this house be, and then each row is a house. And then F1, F2, F3, and so on is what we call features. It is attributes that are the elements we want to separate the houses, or how we want to define the houses. Like F1 could be how big the house is, and F2 could be how far from Oslo is it, or which kind of painting do we have. And then we need a lot of these observations. And we want to make a model that could predict the price. So we make an FNX, which is our model. It could be anything. It could be neural network, support vector machine, random forest. And you have a target. Sorry. This FLX makes your predicted value, right? So your model predicts that this house will cost $1 million. But then, of course, you also have, in the training, you have what it actually costed. So say 2 million. And you have then an error, that is the difference between what you predicted and what's the true value. And then just to declare every row here, every house, then have a corresponding right value, the target that you want to be able to predict. And the error here, or the epsilon in Greek letter, can be divided into 3 kind of errors. The last one here, reducible, is not in our control here. It's based on which kind of model you do or kind of data you have. But we will focus on the other 2. The error due to bias and the error due to variance. The error due to bias is how far from the predicted value you are. As for instance, in the house case, $1 million in this one house. And the error due to variance is when you train your model many times and you retrain your model and you change the input data, the x, between each time. You will get a slightly different model, probably, the f of x. But how much that differs from time to time, from each time based on the input data, that is error due to variance. We will see now how it's graphically explained. The bias here, the blue dots are input data. Don't think about the green line. The red line is my model, f of x. I try to predict the blue dots with just a straight line. The bias here is the difference between the blue dots and the red line, which is quite high here in this example. However, the variance, as I said, if I change the input data, and if I change the blue dots, what will my model look like? If I still just have a red line, I can't do very much. I can move it up and down. So it will probably look pretty much the same, even though if I actually change the blue dots a little bit. Hence the variance here is very low. High bias, low variance. Usually it's a symptom of underfitting, what we call it, when the model is not very complex, almost random. On the other hand, we can do like this. Now we try really, really hard to spot the blue dots. So it's a really, really complex model. In this case, a polynomial of 9 degrees. Here, the bias is actually 0, since we're actually spotting every blue dot. But if we now change the blue dots a little bit, change the input data, the red line will probably look quite different, try to fit every blue dot. So the variance will be very high. And this is a symptom of what we call overfitting, that we have a too complex model that tries really hard to fit the training data, but when you go out in the real world and you see data that you've never seen before, you will completely fail. And that is, this dilemma is what we call a bias-variance trade-off. Is that you can't optimize both variance and bias at the same time. Unless actually if you're a mathematician and you can live in a world where you have infinite size of input data, then you can actually optimize both. And that is not possible in the real world, so we can't optimize both, unfortunately. However, we can, there are some, of course, there are a lot of tricks to reduce both underfitting and overfitting. And there are a lot of theories that you should read about, like how you should have a lot of data, less data, kind of model. But one mathematician, math trick you can do that will reduce your variance a lot is to lower your complexity. And this is, here's when we come over to linear algebra. But the problem here is that we have a function, the red line, is too complex. If it wouldn't be less complex, like a polynomial of lower degree, it wouldn't be too much overfitting. So what we will try to do is to, in the house example, if we have 3 features, we have, as I said, how big it is, how far from Oslo it is, and the last part could be how the number.
Bedroom.
Sorry, bedrooms. Number of bedrooms. Great. So that is F1, F2, F3, and then we have a lot of houses in between. 3 dimensions. We can reduce the variance by instead of taking 3 dimensions, we want to just use 2. And of course, if you say, oh, the number of bedrooms doesn't matter, I just skip it, that's fine, then you have 2 dimensions. But how can you say that? How can you be sure that it's irrelevant? So this is a really hardcore trick that you can do to reduce dimensions, but as everything else in machine learning, the libraries will do that for you, but this is what happens in that black box. So we want to reduce from 3 dimensions to 2 dimensions. But which dimension should we use? And then correlation is relevant. Remember correlation from the statistics crash course? Good. We need that now. You don't have to think about the brick down here. But the correlation matrix is when you have applied this brick on every feature. So it's how does number of bedrooms correlate with how big the house is? How does it correlate with, and we do that with every feature. And remember, the correlation is between -1 and 1. So of course that's important insight in itself. But then we have a matrix. And the nice thing about matrices is that they have 2 important properties called eigenvalues and eigenvectors. Probably heard that we had a linear algebra course. I just thought I will never use that. But it's actually important since the eigenvectors are, you can look at it as the direction of the matrix, and eigenvalues are the size of the matrix in that direction. So each matrix have multiple eigenvalues and eigenvectors. It can have. Mathematically, it's defined like this. If you have a matrix C, an eigenvector is a vector that if you multiply C with a vector, you will just get the same vector, just bigger or smaller. You just scale it. You just move the direction of the vector. So every vector that satisfies this condition is an eigenvector of C, and the scalar, or how much you change V, is the eigenvalue. You don't have to think about that. Again, we do it graphically. If you look at our data, remember the houses, 3 dimensions. The eigenvector, for the first eigenvector, is the direction in this room where you get the most information. And the most information is the direction where you have the highest variance. Remember how much data is spread out? The direction, probably here now, is the direction where the values are most spread out. You get most information by looking at this direction. So this is the first eigenvector. And the eigenvalues of this eigenvector is actually the variance. And this is really important for us. The next one is always 90 degrees on the first one. The direction we should get the second most information, the third one we should get the third most information. Always 30 degrees on each other. So how we actually find these vectors? Again, it's mathematical. Take a linear algebra course to do that. I won't do that now. But it's important is the meaning. So now we have solved it. Let's say we have solved it. We have 3 eigenvectors for this matrix, and the corresponding 3 eigenvalues. And remember that eigenvalues is actually the variance along that axis. So high variance is good. A lot of information, we need a lot of information. And if it's a low eigenvalue, less information, probably means that, for example, the number of bedrooms are so correlated with how far from Oslo you have that you don't gain any more information by taking that element with you, because you already have that information. Or if there's no correlation with the output at all, so you can just skip it. That kind of information do we know at this point. So we choose the eigenvectors that corresponds to the highest eigenvalues, and now we have 2 different dimensions. Instead of 3, we have created our new 2 directions, which is completely different than the first one. It doesn't mean anything for us now. We can't say that this number of bedrooms we don't know. It's a combination of number of bedrooms and how far it is from Oslo and everything, but at least you've got less complexity. And just to move your data from there to there, you should just multiply your input data with these 2 vectors. That's maybe the most heavy math that you get today. Is it fine? Good. The loss function, we have barely talked about it, but I think it's the most important part in machine learning. It's common in all machine learning techniques. You always have something like an error or a loss. The difference between what you predicted and what you should have predicted. And it's common that you always want to minimize it. Or of course you want to reduce errors so that you can perform better. And to do that, you use unconstrained optimization. That's a hard word of saying finding the best solution. Unconstrained just means that if you find a solution, it's valid. You're not constrained in any way. The common part is that you have a function, for example f of x. You want to find an x such that f of x has the lowest possible value. So x star is a solution if there's no other f of x that is lower than that point. Again, graphically, it's the lowest point of f of x. And you can see it. Like, it's quite easy to pinpoint if you have the graph. But usually you have like thousands of dimensions and you can't pinpoint it. In 2 dimensions it's quite easy. So what do we know about this point f of x star? How can we find it? If you remember from math class, the derivative in that point is 0. Yeah, it seems like you remember. So we'll have to go through that. Means that just the direction in that point is not changing. But that is actually true for both the minima and the maxima point. So how do we separate these two? And then we actually look at how this derivative, well, let's look at how this derivative is changing in each of these points. The lower point is going from steep downwards to steep upwards, so in the positive direction. But in the upper point it's going from steep upward to steep downward, so a negative direction. And there we can separate them. So we need to find a point, x star, where the derivative in that point is 0 and the change of the derivative, and it's a double derivative, is greater than 0. And bear with me, more dimensions. We get a new Greek letter. The man explained to us the lambda, which is just the derivative, but in many directions. So instead of just df dx, which is we have in one direction, we need a vector in each direction, each dimension, and we take the derivative in both how many bedrooms are there, how far we are from Oslo, and how big is the house. And we get a 3 vector instead of just one number. And of course you can, as you see, we have a double lambda and it's positive definite, and it's starting to get a lot of math there. So could we do this easier? Yes, we can. You don't have to actually solve these equations. Of course you can do that, but it takes a lot of time. So instead, we try to find an approximate solution. And this is an example of graded descent, which is quite common in many machine learning techniques. So here, if our function, you can think that is actually the error function, which we want to minimize. And the axis here depends on the method. For example, in neural networks, is the weights. The weights in a network, if you're familiar with neural network, are the parameters, the variables that we can adjust. So how do we adjust those variables due to the error function? And then we need to actually find the gradient. So we start out at one point, we calculate the gradient in that point, and then we move in a direction where the gradient is lower and where we gain the most from the error function. We reduce the error function the most. And we take a step in that direction. And that step, the length of that step, is a hyperparameter in many machine learning techniques known as the learning rate, which you're probably familiar with. That is how far are you going in each step. And you will, depending on the method, but usually will go until there's no such point where there's any improvement, then it will stop. The same for many dimensions where you have, instead of a graph, a plane, and you move downwards down the hill. But if there's more than one minima, how can you be sure you get the best solution? And you actually don't. Like here. There's at least two, maybe 3 minimas. How can you be sure you're going down there, which is probably the best, and not down here? And there are some techniques to do that, but maybe the most important is the learning rate that you set. It should be low enough that you actually don't move out from the best minima. It should be high enough so that if you start here, you don't just jump down there and then you're fine. You actually have a high enough learning rate, step size, to get all the way down here, or all the way down there and then down, down, down. Yeah. So just experiment with your learning rate. It actually does matter a lot. But if you were awake, you see that you still had to derive the error function to actually calculate the gradient in each point. So even though we didn't have to solve all the equations, we still have to find the derivative of the error functions, which is not very simple in itself. I'm not going through that now, since most of the libraries are doing that very well. TensorFlow, if you're familiar with that, is actually optimized to kind of calculate that that gradient in the backpropagation algorithm. But if you want to understand the backpropagation algorithm, I suggest you just recall some of the chain rules we had in calculus. Finally, some probability theory. A new quiz. Unfortunately, there is a new cancer in town. And you know that 4% of your population is getting it. But luckily, we have a test to see if you have the disease or not. It's always diseases in statistics or probability theory. But of course, the test is not 100% sure. So if you are sick, there's still a chance of 5% that the test will say that you're healthy. And if you are healthy, there's still 5% probability that you actually are sick. Okay? Understand? So now say that you took the test, and the test said you are sick. What is actually the probability that what is the probability that you actually are sick? Or in other hand, do you think that most likely you are sick? How many of you think that? Of course, that was a trick question. I know. Yeah, good. Thank you. Somebody who guessed the probability.
So 50%.
Yeah, 40% chance that you are sick. 60% chance that you are 45% chance. Yeah, that you are sick. So most likely you're healthy. And again, it's kind of covered in the amount of people that are healthy. But we'll see how we could calculate this probability. But first, what is actually, we denote the probability of an event S to happen like this. P of S. For instance, if you throw 2 dice, what is this is how we denote the probability that the sum of the i's is 7. I don't know what it is, but at least I know it's higher than probability that 2 i's sum up to 2, since there's a lot of more combinations to end up to 7 than to 2. And again, we see the probability distribution. Remember from the statistical crash course. The probability for each event should happen. The more used, at least in both statistical models and in, I don't know if you have heard of restricted Boltzmann machines, which is a kind of neural network for at least unsupervised learning. Use joint probability distribution, which is the possibility that both x and y is happening. And we look at an example. So what is this probability that I voted for Trump and that my last Twitter had a spelling mistake? So let's assume I can separate the population based on this. Like we actually have distinct groups. I know it's not as simple as that, but say that we can divide the group or the population based on if they voted for Trump or not, or if their last tweet had a spelling mistake or not. Of course, I think every presentation in 2007 will have a Trump joke, so it's not. So the probability that both of these things happened is the same as the probability that I actually voted for Trump. And given that, let's see I actually voted for Trump, what is then the probability that my last tweet had a spelling mistake? And this part here is really important, because instead of just looking at probability of my last tweet, if it has spelling mistakes or not, and instead of looking at the whole population, we're just looking at the people, given that I voted for Trump, then what is probability that my last tweet had a spelling mistake? Which is the same as just the order. Probability that my last tweet had a spelling mistake times, let's see that had actually happened, then what is my probability that I voted for Trump? And if I just move, these are the same, I just move that line up, just clean up by putting the first element there on the other side, and there we got Bayes' theorem, which is actually a machine learning technique in itself, but also used in many other machine learning techniques. And it says that if you tell me how many people voted for Trump, and how many tweets did have a spelling mistake, and among all the people that voted for Trump, how many of them actually had a spelling mistake in their last tweet, then I could tell, based on your last tweet, if you voted for Trump. And this is just the same for many dimensions. Always many dimensions, because in machine learning you also have a lot of data. So it's just chained, or it says the same. Then again, we got this Greek. And of course then we get some help from our Greek friend. This is the letter pi. And pi is almost the same as sigma, just instead of adding the elements, you're taking the product to multiply them. And again, of course, you can specify which elements you want to multiply. I think that is most of the notations you need to read hardcore deep learning papers. So I think actually I spoke really fast. This is actually every part on this script from the crash course through linear algebra and how we went from 3 dimensions to 2 dimensions, and in that way reduced the variance and made hopefully a better method, or a better model. And then how we minimize that error in the method, and finally playing with Trump. Hopefully you see that this is nonsense, otherwise we will take this all over again. But actually, my last tip is, as I said in the beginning, you don't need to know much math to just get started with machine learning. So my tip is just start making your model, use the libraries, and when you're curious about something, then stop. and read about it. Don't take a linear algebra course now. But it's really fun when you do. So. Thank you, that was all I had.
Like the example very much that you showed here. Kind of makes sense. But I'm just wondering, can you give another, because it looks like it's something you can use very quickly to figure out probability or assumptions in a fairly quick way. Can you give some other examples other than Trump and tweets?
You don't think it's realistic? It's very common use actually in spam filtering or detection in text. So, like, for example, if, like spam filter, an email. So, can I use the book like this? Because otherwise I think I'll just talk. So P-O-K-A-D times P of U-A times P of P. So probably there you see, given that I have a word, for example, is always used Viagra, so for this example, given the word Viagra in an email, what is the probability that, what is the probability that it's a spam mail, a spam, given that Viagra is in the email? And in that way, this is just a rule that if this is higher than 50%, you will send it through the spam filter. And then you just have to learn a lot. Of course, then you just need the probability of Viagra and the probability of spam filters. You just have to count a lot of emails. That is easy data to gain. And then you need the probability of Viagra given spam filter. Again, you just have to look through a lot of emails, counting words, see how of all the spam mails we have, in how many of them does the word Viagra occur, and then you have the probability, the ratio.
It's a good example for maybe for current data, but is this used or can it be used for future predictive analysis? Like, can you predict using this base theorem as well, or would you use something else?
And I definitely would use regression algorithms like neural network or decision trees, I think. So this is, I think actually in chatbots, they still use base theory to classify if you have correspondence with a customer and you are curious if it asks about A or B, like if you ask about when the train leaves or where the prices are, then you use kind of these techniques. I think that is most common base theory.
Thank you.
Anyone else? Thank you.
Thank you. So I know it's kind of a heavy topic, right? Mathematics. Why doesn't everyone just stand up for a second and maybe just stretch a little bit, move around? I know it's late, it's Friday, right? You're joining us on a weekend, and we know that's really odd here, so we really appreciate it. Yeah, just get up, move around a little bit. We'll let any latecomers kind of filter into the room. If you want to run to the restroom or grab a drink. So I think we can go ahead and get started again. So a few things we forgot to mention earlier. We do have a hashtag if anyone likes to tweet or is on Twitter. You can just do hashtag DemystifyAI. All of the organizations here also have Twitter profiles. So for me, that would be at AI Accelerator. You could do at Noroff. Does Nordic Impact have a Twitter? No. Okay, well, Catapult Accelerator maybe?
Yeah, of course.
Yeah, at Catapult Accelerator? Yeah? Okay, perfect. So yeah, if you would like to tweet along any pictures or phrases, that would be great. We appreciate it. Also, if anyone needs to get on the Wi-Fi, you can get on Noroff Guest, and the password is noroff.guest with an exclamation point. So I can pass this around too if anyone needs it. Yeah? Okay. And then we're going to go ahead and introduce our next speaker. And by the way, these slides will be distributed after the workshop. So if you would like to refer back to them at any point, they'll be available to you. And for this specific presentation, it would be a little hard to code along with the presentation because it's going to be going kind of quickly. But again, if you'd like to refer back later on, you're welcome to do that. And I'm going to probably say this wrong, but we have Hakkon, Dissen, and he's a technology analyst with Itera, and joining us today. We'll be talking about Scikit-learn for machine learning, as well as Python and NumPy.
Right. So, welcome to the talk about how we test our ideas with Scikit-learn. First, we're going to start with talking about what Scikit-learn in general. I'm not sure how many of you are familiar with Python. Python has a few caveats, so I'm going to go through those quickly. Then we're going to move on to looking at the other building blocks of Scikit-learn. I'm going to abbreviate it sometimes as Scikit-learn. I hope that's fine. The developers themselves do that a lot. If you look around their GitHub or the documentation. We're going to talk about NumPy, SciPy, and Matplotlib. Should be familiar for some of you if you've worked with this before. Then we're going to take a quick detour into machine learning essentials. Now, I have a computer science background and not a maths background, so no Greek. Then we're going to look at the API of Scikit-learn. We're going to look at 4 interfaces, even though there are technically no interfaces in Python. And then finally, we're going to talk a little bit about parameter selection, and that's going to overlap slightly with the previous presentation. So first off, Scikit-learn, they define it as machine learning in Python. It's like a big quote they have on their webpage. I think it's easy to use, and it is fast, so those two together should be good. Again, it's Python, but it's fast. So Python itself is quite a slow language, and we're going to talk about why that is in a few seconds. Scikit-learn has a very good documentation. So if you go on their webpage and you're wondering, okay, how does this model actually work, there will be normal software documentation for the model, and then there will be a user guide which tells you more how it works and how you can sort of look inside the model and try to understand what happened. And finally, it's supported by Azure machine learning. Many people think that that's important, whether it can run in the cloud. And if you run Python on Azure, they generally have something called Anaconda loaded in for you, where you can make that happen yourself. And Anaconda is just a Python distribution that has Scikit-learn within it already. So if you're on Windows and you're having troubles installing Scikit-learn, Google Anaconda and install it. It's one .exe installer and not 3 hours with compilers and pip. So bullet points with Python, it's mature and it's used by many. So it's kind of old language. It's not C++ old, but it's old. I think it's started in 1990, and it's used by many, not just data science people, but everyone uses it. Almost all of you who have had some computer science education have at some point used Python, I think. It's it's the most popular language on Stack Overflow right now for data scientists. If you look at the latest polls, it's dynamically typed, so you never have to worry about the type until runtime when it crashes. And Flux is turning in. Machine starts lagging. So where was I? Yes, it's dynamically typed, and the big, I think, reason why it's slow is because it's interpreted, which means that you never compile Python code. You'll find .pyc files. They're not compiled Python files. They are just Python. It just helps the interpreter load faster. So if we walk through a block of code in Python, it's not bytecode that the interpreter will see a line of code, read that line of code, and then do that line of code, and then do the next line of code. It doesn't sort of optimize very much beforehand on what it's supposed to do. So, yeah, that's slow. Everything is an object, which means that if a function is an object, a class declaration is an object, so you can house it around. Things have fields. It's very useful, and we'll see later why that's sort of useful for this. Moving on to NumPy. NumPy is a mathematical library for Python. It is the library for storing arrays or matrices, as we talked about. So in this presentation, I'm going to use it to store observations in single vectors, and then those vectors in a matrix. NumPy speaks about them either as n-dimensional arrays. So when you do this, you need to know that there are n-dimensional arrays which can have any amount of dimensions. And it also has sort of a wrapper around n-dimensional arrays, which are matrices. There is no real difference, and Scikit will often just accept either and return whatever it wants. But just know that there is a slight difference in what they can do, how they deal with operator overloading. NumPy has been implemented in C. It is fast. It is a lot faster than doing something in Python. So basically, what they've done is they've written everything that takes time is written in C, and then they've written connectors to Python for that code. So if you want to do, you can do something from Python which is easy for you, and the machine can do it super duper fast, which is good for everyone. So, and it's fast, as long as you use it right. You can use it wrong. I'll show you a quick example of something that's way faster in this language without using linear example. So if we have a large array, say it's 10,000 by 10,000, and in Python we want to zero every part of that array that's smaller than 0.5. I'm not doing a special notation from Python, even though I probably should in this case. So basically, you'll have to step through this double for loop a bajillion times. I've actually done something wrong. You need to do the length of the array and not just the actual array. Oops. My bad. And then you have to index each part in the array, check if it's smaller than 0.5, and then assign that something. That's normal Python. This is slow. This is NumPy. Basically what you do is you say, I didn't speak about did I speak about operator overloading at all? What it is and how it works? Okay, so basically NumPy has defined what happens if you take an array and say a size comparator with a number. That will just give you, say this is a matrix, it'll give you back sort of a mask matrix that is the same size and the same dimensions, but for every number that was smaller than 5, that'll be true, and for every number that doesn't satisfy this, it'll be false, right? And conveniently, they've also overloaded this operator, which is the indexing operator, so we can say, okay, for this array, we can try and index every element that is true in this mask, and then assign it. And because NumPy deals with everything here, you just tells us what to do on this operator, and they've decided what happens when this operator is used. This is fast because it can be done in C, and the interpreter doesn't have to step through this mess. Understood? Yes?
Is it overwriting the array in there?
Sorry?
Is it overwriting the array? Because is that the same way?
Yeah. Well, no, it's not overwriting the arrays. It's changing the underlying array.
Yeah.
So yeah, yeah.
Okay.
No, but that's a good point. NumPy arrays are mutable, which means that they can be changed. Functional programming, or sort of the concepts around that, are a bit outside the scope of this talk, but just know that they can be changed, and you don't have the double memory. You don't double something when you do something with the array, which is very useful because they can be big and take a lot of memory. SciPy is, they call themselves the fundamental library for scientific computing. I like to think of them as what NumPy isn't. There's a bunch of mathematical methods in there that you can, if you have a matrix and you want to do something that's more maths than it is machine learning, look in the SciPy documentation, and generally it will be there somewhere. So it builds on NumPy, and by that, the important thing is that it uses NumPy's data structure underneath. But as someone who develops this data, if you want a new mathematical function to be put into the Python universe, put it in SciPy. The only reason why NumPy actually has any mathematical functions is because it's supposed to be backwards compatible when people didn't use SciPy. A good example is something called sparse matrices, which is sort of a data representation thing, but it's still in SciPy. And you'll have this problem if you want to, say, make a recommender system or many other different machine learning problems. You'll have this big matrix, and this is just like the house, or the houses with the different features. These are the users, and sort of the feature vector is how much do they like each item, right? So say these are users and these are books, and we want to recommend you books. At some point, you'll have this matrix. And this matrix has a lot of zeros in it. And when a matrix has a lot of zeros in it, we're sort of repeating the same information a bunch of times, because we're interested in knowing how these numbers are different. But when something is zero, it's just zero. And if you store all these zeros, if you take 32 bits and you use that to say that this is a zero, when basically if you have like 10,000 users, 98% of all the values will be zero. You're wasting a whole bunch of memory, and things can be computed a lot slower on it. So just know, because I burned myself a lot on this when I first started using Scikit and linear algebra in Python. Just know that these exist, and if you have a lot of data, use them. If it's sparse. If it's not sparse, then don't, obviously. Right, so no big segue, but we're now going to define what classification is. We've sort of now moved on to the what is machine learning bit. So an important concept is classification when we're trying to find which label belongs to which observation. So for instance, this demands that we have, I don't know why I said often, this demands that we have labeled data. Okay, so an example here is what is this a picture of? This is from a data set called MNIST. How many here have heard of MNIST? Okay, so cool. It's basically handwritten digits, and it's super useful to have this data set because there's written a lot about it, and you need to know what it. You should know this data set if you wanna try things, because most introductory material will use this data set. Actually, a lot of them do this. So there's a handwritten digit, and so the feature here, for instance, you can find lines in this picture. That's sort of up to you. How do you want to do feature extraction out of the observation? But let's say the feature is what color is each pixel. So that would just be a long vector of that. And then there's a label, which is the number that it actually represents. We're going to use this for the example later on. So remember that. Regression is when we're trying to do continuous values. It's very similar. Basically, it's almost the same thing. So basically, you're trying to look at things that vary instead of things that either is or isn't. So if you're doing weather forecasting, you're trying to figure out a temperature, which is a number on a range. It's just, same thing, just different. Or stock prices. So just know that when people are talking about regression, it's generally finding some continuous value. And when they're talking about classification, it's generally some class, like which bucket do you fit it. Finally, this is clustering. And here we don't talk about labels. Regression, you also need labels, by the way, but it's just a continuous label. For clustering, you're looking to group similar data points. So say that these are people, and we've projected them into a two-dimensional space. And the features we've extracted on these people are what kind of music do these people listen to. Okay, so we want to figure out what groups, sort of how do these people group together, and then start doing interesting things about that. For instance, if we have this guy, we should be able to recommend him music for people that sort of lie in the same area in that sort of feature space. So yeah, that's one use for clustering. There are a million uses for it, but I think it's the most intuitive one. Okay. Any questions so far before we move on to Scikit? I'm good at explaining things. So the Scikit-learn API. It has 4 sort of main interfaces, which are the estimators, the predictors, the transformers, and then a pipeline, which is sort of more a meta concept than it is an actual interface. Before we do that, though, we're going to talk about the dataset we're going to use. I lied when I said we were going to use Analyst because I couldn't. The place Scikit downloads datasets from for you is down. It has been for the last week. So we're going to use one of the included ones, which is just the numbers dataset. It's basically just the same thing, just with a lot less pixels. But in this dataset, you should know that each picture is made up of 8 by 8 pixels. You can't see the white pixels because it's white on white. So, sort of reiterating what we did last time, we have to extract features. So we take all of these pixels and we just make a vector out of them. Right. So this illustration is actually from a neural networking example, where you would sort of find connections between, but the general idea is still good. You find connections between the different features and sort of which bucket should we activate, which bucket should this feature fit in. We're not going to do neural networks in this talk because Scikit is not super duper great on neural networks. But this is the important part. That's how we make the feature, and this is what's going to be inside our code. So when you're in Scikit-learn, we're going to load this dataset, which is extremely simple. You just say datasets.load digits. And then we're going to split it into a test set and a training set. So the digits just come in sort of the digits objects which have all the images. And then we're going to use NumPy to reshape them. This isn't important. It's just basically, it used to be a three-dimensional array, and we've made it into a two-dimensional one, just by taking, because it was 1800 images just layered on top of each other, and we've just sort of squashed that into one matrix with 64 pixels this way. Just read up on that function for this kind of stuff. It's useful. And then we're defining a cutoff, like where in our data should we, what should we train with and what should we test with. So I'm not sure if it was covered in the last presentation, but basically you take, let's say, half your data, and you say, okay, this part of my data I'm going to use for training my model, right? But so that model will be biased based on what data you gave it. So if sort of a signal is in, if you overfit it on this set, right, it will fail on this set, with this set, the test set, because we haven't shown the examples in the test set. We're just going to use those to see like how good are you actually. Yeah. This is slicing for those of you not familiar with Python. How many of you are familiar with Python? Okay, cool. Oh, that's one thing. I said that you should probably have programmed a bit before you saw this, but I never said anything about Python. So if there's any questions about Python, or any questions in general, just raise your hands during the presentation, because it's a lot easier. It's a lot easier to explain it while I have it up. And if you're wondering something, then everyone else is wondering the same thing. Now we're going to talk about estimators, which is sort of I think the most important interface. These are all learning algorithms. Today we're going to look at a support vector machine. What they do is they fit the data, meaning they take the data in, and then that object becomes sort of a model and exposes methods we can use later. And it has this, they all have a score method, which we're going to look at later. But this is an introduction, and how do you choose an estimator? Because there's a bunch. I think this is actually a very good way to do it. So if you have no idea what an isomap is, and you wonder if it's applicable to your problem, if you have a problem and you don't want to try an algorithm, or you have a problem and you need to find an algorithm, go to this URL. Just order to Google machine learning map, and then we start. And we have our data set, so let's do the exercise here. Okay, so we have more than 50 samples. We had 1,800. Are we trying to predict the category? Yes. We're trying to predict which number was written. Do you have label data? Yes. We have the actual numbers that correspond to each handwritten digit. All right. We have less than 100,000 samples. Yeah. Okay. Use a linear support vector classifier. Okay. So what is a support vector machine? This is taking a bit away from Scikit, but a friend of mine told me I couldn't use one without explaining what it was. So basically, you have two classes of data, and you want to draw a line between these two classes and say that everything that lies on this side of the line, that is class 2, and everything that lies on this side of the line, that is class 1. And this will be, if you read more about this will be referred to as a hyperplane, because this is generally not done in 2 dimensions. For instance, in our case, we had 64 different features, remember? So we're going to do this in 64 different dimensions, unless we do dimensionality reduction first, but we're not going to do that yet. So how do you place this line? Well, what's a good way to place this line? Any ideas? No one? Right. Is it good now? Oh, now? Yeah? Pretty good. Is it better now? Why is this better than this? If you can see the difference.
Well, actually, they're the same.
Yeah, they classify this the best, but with the support vector machine, we're assuming that if we can make this gap as large as possible, then we have the best line we can get. This example is linear. Support vector machines can also do unlinear stuff, and by linear I mean that it isn't half red in here, and then you sort of have to draw a circular line. You can use something. use some funny maths to make this work in a non-linear way, but that is definitely beyond the scope of this. But this is basically what we're doing. We're drawing a line. And then the star and yellow are because they're the most important and because I didn't actually make this figure. But so basically, the closer something gets to this line, the more it affects this line. And the closest ones being the most important one. Just think about it that way. So how do we make one in Scikit-learn? We import it and initialize it and fit it, and we have one. That's the good thing about libraries. We can just do this. So this is a hyperparameter for this class. There's another class that basically starts with this hyperparameter. Hyperparameters was like when she talked about gradient descent, like how far should you jump. This is basically the same thing, just meaning sort of what sort of problem are we solving? Is it linear, or is it not? So the classifier is an estimator, so it has the fit method. So we give it the training set, which was this large matrix of features and observations, and we give it the labels, which was just this long vector of what for the first row in the matrix. Which number is it? Was that clear? Okay. So we now have a model, because this gives us a model. The classifier has now been fit. And those models, if they're a predictor, they implement the predict interface. So that means that it can be used to predict something new. And it returns a vector that is just like the one we gave it when we trained it, that gives us labels. This one just tells us about how it predicted it. So if you want to predict, this vector will be on the exact same shape as this vector. Just it would only be as long as this matrix is long down. So this is the test set. So what we're basically doing now is we're giving it the matrix of all the observations we haven't shown it yet, and asking it to, okay, I'm showing you all these images, predict their labels. So, okay, how do we measure the performance of this? Like, will this work? There are a couple of built-in ways that are simple to understand and cool. This is the classification report, which just comes from a module in Scikit-learn. We have precision, which is basically how good are we hitting. We have recall, which is basically are we hitting every. So of the things we predict, of the labels we give something, how often is that correct? And out of all the ones we should have hit for this number, so when we're saying 0, how many of the zeros did we find? And this is in the training data. And the F1 score is just a way to combine this. Remember the F1 score, but it's just a combination of the two, but we're going to use it later. And then another way to look at it is a confusion matrix. This gives you more detail. So in our example, the model we made, when it was supposed to find the number 3, found the number 3 79 times. However, it also misclassified a 3 as a 5, a 3 as a 7, and a 3 as an 8. And this can be good to sort of understanding your data, and looking at this you can sort of understand, okay, which when it's a lot less trivial example, this is useful for understanding what is hard to classify and what mistakes are my model making. And to do this in code, again, because it's a library, it's so simple. It's simple. So we have the test tables and what we predicted. You import the metrics module from Scikit-learn, and then you just basically say, show me a classification report. and you print it, and then you say, okay, show me the confusion matrix, and you print it. And this is why Scikit-learn is so cool for testing our ideas. For if you think, will this work? It's so quick to put together sort of the algorithm, the workflow, and the code, and then just looking at it with your own eyes, you can just, okay, it's awesome. So another thing you can also use is matplotlib, which is also built into Anaconda. It's useful for visualizing the data. I say it's powerful with Scikit-learn's inspectability. They have a concept of inspectability, which means that every model you make, the parameters inside the model that define the state inside that model should be inspectable by you. So it should expose it by some function or some field on that model, on that object. Will generally expose it to you, so you can look inside and see what happened. And then you can plot it using matplotlib. Matplotlib can make all sorts of plots, but this is how I made the clustering plot I showed you earlier. Okay. Transformers. Transformers have it's the idea that you have some data and then you change that data, and so it's a new set of data. It's useful for 4 things. Pre-processing. That's when we take in some data and then we change it, so we think it's going to be easier for our machine learning algorithm to use. We have feature selection, which is basically we take in some data. Oh, there's too many features. For instance, in the picture, we should never look at the rim of the picture. You can use feature selection algorithms. I'm not going to go into them here, but they exist, and they exist in Scikit-learn, so find them and use them to see what features are important for what we're going to do. It's generally the same for a lot of different estimators. So yeah. There's feature extraction, and there's special mention for feature extraction. Sorry, is it's basically when you have some data that isn't useful, and then you try to extract some features from it. And then dimensionality reduction is like she talked about, where she used PCA to do it. You take data from a space with a lot of dimensions, and then you project it into a smaller space. These transformers, they implement theta transform, but I'll show you in code. So I was going to show you principal component analysis. So just to refresh from what she said, it's basically you have a line and you have points, and you want to put that line in this space so that you have the highest amount of variance still. So you want to go from 2 dimensions down to 1 dimension. So I'm not going to go into why this line is here, but just know that when you do this, you sort of it's the best way to reduce dimensions, or it's a good way to reduce dimensions while still keeping your data points separated enough that we don't lose sort of the signal that's present. And if we want to do this with a transformer, we just load it in from Scikit-learn again. This is probably becoming boring at this point. We say decomposition though. PCA, we define how many components we want. We use that fit method that many of these have, and then you just call the transformer and you get the new X, which is this data just in pure dimensions. Finally, we're going to talk about pipelines. Pipelines are just they're just a way we use to chain transformers together. So because an estimator is only sort of the last thing we do, we first need to transform our data in many different ways. Scikit-learn has a way we can sort of create a list of all these transformers, and then so you create a list of these transformers, and you say which parameters they should have and so forth. And then you call fit on sort of on the pipeline, and then as soon as it's done, it exposes the method of the estimator app. So you sort of all the okay, I'm going to take my data, I'm going to put it in this transformer, I'm going to take it out again, and then put it in this transformer, and take it out again and put it in this transformer. You don't have to do all that complexity and boilerplate code yourself. It just goes through the pipeline and becomes an estimator and maybe a predictor of what you have at the end as a predictor. Now we're going to take a slight detour into hyperparameters. So it's defined as parameters that define how the estimator is trained or fit to our data. They're very important for performance. Like in the gradient descent example, if you jump way past a minima and just start going in another direction, it won't work. Scikit-learn has the notion that it should provide reasonable defaults. So if you just make an estimator, the defaults, if you specify nothing, will generally be good. If you start toying around with them and you don't know what you're doing, they'll quickly turn bad. But Scikit-learn has a very cool way of helping us find the best one. It has two main ways of helping you find them. And the easiest one is just a grid search, which basically means try every combination. But it can do that for you. So what you do is this. You give it, okay, which way do we want to go? And it's a dictionary. It's similar to an object in JavaScript. You have a keyword. Okay, so for the kernel, which was one of the parameters, which is one of the arguments for the constructor, because you have named arguments in Python. So that's a named argument of the constructor. You say, okay, I want that to be linear. And if that is linear, I want C, which is another constant. C in the M says how badly do we penalize you for making mistakes. Like while you're training, if you move the line wrong, a point is on the wrong side, like how much should that count? Because in normal data sets, things won't be easily separable. So you give it some range of C's that you want to try, and then we have another kernel. And the kernel is basically, an RBF kernel it does that trick I talked about where we move from a linear to a non-linear space. So we get to try both on our data. And then we have another parameter, we have the same parameter C, sorry, and then another parameter gamma. And what it does for you is you specify I want to do a grid search. You give it the estimator that you're going to use, and this is very useful because it allows you to sort of try. This can be replaced very easily, so you can try a slightly different estimator, and then you give it a scoring function, like how should I score this? And this was the F1, which was the combination of precision and recall, and then you give it something that tells it how it should validate those scores. It doesn't just do a simple split in the middle of the testing and training data. It splits it into many small segments and then sort of rotates which ones it uses for testing and training, so you'll get a much better.
Is it like a batch size or temp? Or?
No, that's not a batch size.
Okay.
That is a k-fold size, or a cross-validation parameter. So you take your data, which is, if you imagine your data as a long line, each data point is 1 point, and then you make sort of 10 slices in that line. And okay, these are our 10 different data sets, and then we alternate which one is the training set and which one is the test set, and we get sort of a better average, or more representative average score. Then you fit it with your data, and then the reason you don't give it the whole data set is because there may be some bias between this data set and which set of hyperparameters is better. So it's sort of the same notion why you split the data when you're just doing this normally. And then this again exposes the best scoring one, which you can now use for predictions. So let's take a more real-world example. If you don't know how those parameters should be, but you know that they can change given your input data, and your input data is historical, so it changes all the time, but you want to make a system that can stand, so you don't have to go tune the parameters every day, you can try and set up something like this, and you can automatically find the best predictor, and it'll expose that for you. So to sum up, we talked about Scikit-learn. We talked about sort of what's important, what's the three main things we do in machine learning, and then we talked about the Scikit-learn API. That's the presentation. Thank you for listening, and please, questions.
Yeah, the group search, is that just trying all the combination of those parameters?
Yeah,
there's no intelligence in there?
No.
Okay.
There is a better one. The name escapes me, but there is a better one. It's in sort of this, yeah, it's in there. It does something a lot more clever. Anything else? Okay, cool.
We have now reached our final session tonight, and it's going to be hosted by Laura Montoya, founder of Accel.ai, who you've already met, and we're going to do an exciting collaborative live session. Yep. So, warm round of applause.
Okay, so you're probably wondering if you know anything already about machine learning. What about this is artificial intelligence, right? I think there's been a lot of buzzwords in the industry recently about what AI really is. And in a lot of ways, machine learning is artificial intelligence, right? And deep learning is artificial intelligence. And so what I really want to do in this next section is get you to think about the real-world applications, right, of machine learning and deep learning. And we're going to do that by doing a little bit of research and then presentations on algorithms, okay? So you've learned a lot about algorithms tonight, but we're going to go and dive in a little bit deeper. So what I'm going to have everyone do is stand up, and we're going to break off into groups. And so we're going to want 6 people to a group, so what I'm going to do is just have you count down the line 1 through 6. Okay, so we're going to start on this side.
1, 2,
What are we doing?
Just counting down 1 through 6. No, so he was 5, right?
6.
6,
1, 2, 3, 4, 5, 6.
1, 2, 3, 4,
1, 2, 3, 4, 5,
6, 1, 2, 3, 4, 5.
1, 2,
3, 4, 5, 6.
1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1.
Okay, great. So now we want everyone to get in their respective groups. So can we have group number 1 over here in this corner? Group number 2, how about like over here? Group 3. Group 4. 5, and then kind of 6 in the middle.
Ja, det er ikke superekspert.
If one person from each group can shout out your number or hold up your hand with the number, it'll help people. Oh, what number? Okay, 56 was okay, so once everyone is in your group, everyone's group 5, I think it's all the way up here.
6.
Okay, great. So yeah, definitely introduce yourselves to each other, get acquainted. I'm going to come around and I'm going to assign each group an algorithm. We're going to have this algorithm. First, Not yet. Okay, so the point of this little game that we're playing now is you've been assigned an algorithm. You're going to have 20 minutes to research that algorithm, okay? And then I'm going to give you post-it notes and markers and sticky boards. And what you're going to do is you're going to find out what that algorithm means, what the math calculation is, how it can be applied in the real world, and I want you to apply, to bring back at least 2 examples of how it is used. Okay, and so these encompass machine learning and deep learning algorithms for artificial intelligence. And so you're going to want to then come back and do a presentation as the group on what you learned. Okay, and when you present, I want you to try to explain what your algorithm is and how it works, as if you were explaining it to a 10-year-old. So try to simplify what it means as much as possible. Does that make sense?
Yeah.
Yeah? Okay, perfect. So if we can have one representative from each group, we'll come and collect some post-it notes, some markers, some sticky paper, and then you can go off into any room that you'd like within this area, take a laptop, and I'll give you guys 20 minutes, and then I'll come around and give you warnings when we're ready. Yeah? Sound good? Okay, great.
Different ones.
And that will be I think Adrian will show us the groups so we can actually work together there. So, yeah.
If you don't have one.
Sorry, we got sent out too early, so we didn't get the first part.
Nei, ikke skjønte noe ting av hva vi skulle snakke om. Alle liker blanketter. Det er morsomt, da. Prøve å liksom komme til faen, hva er dette for noe?
Altså, det er noe med det der å kunne snakke om det utenfor at det er en abstrakt data-greie.
Ja, det var det. Jeg vet ikke hvor mange folk kunne rundt meg, men jeg kan ikke noe særlig der tatt. Men det var sånn, alle som vet litt på klassen, og hva er det ikke å si her? Jeg har ikke feil.
Det er bare starte siden for å se hvor man
Men skal jeg da alltid til, for jeg følte liksom nå begynte å få litt grann at du kunne og det er ganske morsomt å sette og jobbe sammen og prøve å forstå egentlig.
Jeg synes det var litt sånn når jeg forstår, nå skal alle sammen opp, å nei. Min instinktive norske reaksjon var
Jeg skal nok ned til.
Vi vant, Tara. Henrik og vi vant. Vi kan drite med om Random Forest.
Random Forest, ok.
Ja, du har
det høres jo rart ut. Nei, jeg lærte om Deep Belief Networks. Det var ganske spennende. Jeg vet ikke om jeg kan...
Ja, hopp inn.
Du hadde gjort dette på forhånd?
Ja, ferdig program. Ja, en demo her nå, så jeg stemmer på.
Vi gleder oss.
Jo, da blir det
Okay, is everyone kind of settled in? Yeah? Great. So, how was that? What'd you guys think? Just doing a little research? How did it feel? Good? We got some thumbs up? Yeah? Anyone feel kind of scared or intimidated about digging into these algorithms?
Yeah.
Yeah. And it can be really intimidating when you're learning a new subject and you're not quite sure. And there's a lot of mathematics, right, if you're not comfortable with that. You know, and there's a lot of buzz around what this means and how it can be applied. So this is just a nice example to show you that really these things aren't that scary as they might seem. And oftentimes if you just get together with a small group of people, you can easily just do a little research and learn way more than you thought was possible. So with that being said, we're going to start calling up the groups to do a presentation on what they learned for the rest of the class. And what I will ask is if there was an individual or two that was more experienced and kind of lectured the rest of the group, that they not be the ones who present. We want those that learned to really convey what they learned in the best way that they know how. So again, if you can include what your algorithm was, so the name of it, a description that you learned, and then one or two real-world examples. And again, if you try to break it down as simply as possible, as if you were trying to explain it to like a 10-year-old, would be helpful. That way everyone can understand, since they didn't have, you know, Wikipedia or whatever, to kind of bring them up to speed. Does that make sense? Yeah? Okay, perfect. We can ask the first group to come up and start their presentation.
Okay, so don't pay too much attention to this. It's just some we got decision tree as our algorithm. So I'm just going to say just short what it is. It's an algorithm that's often used to solve classification problems. So you train it on input where you have features, like we have talked about this. For example, let's say you want to
go to a restaurant. The restaurant have different attributes such as prices, what type of food it is, location, and so on. And what the decision tree does is that it tries to you feed it the different attributes that you want to try to label to an answer, and it will go through the nodes in the tree, and for each node you make a decision and kind of break up the possible solutions for a label. So in the just to mention a real-world example, how it would work for a restaurant, you could start by, for example, selecting a node that asks what type of food do you want. That could be, for example, Italian, Chinese, Thai food, and based on what the observation for your kind of queries, your observation is, it will choose the next level in the graph. And at that level, you will ask another question, which could be the price range. Is it cheap? Is it expensive? And you continue down until you end up at an actual restaurant in this case. So that was a real-world example. We're actually going to have a live demonstration of a toy problem, kind of, where someone has seen someone do something bad. They have shoplifted, and they didn't know the person, but they got some description of that person, and we're trying to label our usual suspects here that are often doing bad things to find out who did it. So in our tree, our first node is, did the person have glasses or not? And the answer to that is yes. So like all the possible labels, that's what we start with. But once we have asked that question, we split into the ones that are still possible values or not. So we are left with these 4 people. The next one is hair color, and the possible solutions in our model is blonde or dark. And the witness says that the person had blonde hair. So now we kind of are getting closer to a solution. The last question is, in our case, is gender, and the witness said that he was a male. So that was the culprit. So again, this is a kind of toy example, but it shows how the decision tree works, and yeah, you make decisions and you get closer to a solution.
Thank you. Any questions? Was that fairly easy to understand? Yeah? Okay.
It is a very easy algorithm.
Yeah.
Well, it's easier to explain how it works than how you actually build it. But,
fair enough. Yeah. Thank you. Okay, group number 2, please.
Hello.
Er vi jo supposed to, skal vi alle stå der? Ja, jeg viser at du er en del av støtteplassen. Hakkon.
Do you want to start?
Yeah.
I can do the layman's explanation. So I can do it. So I mean, you guys have just explained the decision tree, which makes to go from trees to forest quite sort of a easy evolution. So random forest, as far as I understand it, at least, learning from Sundara and the others here, is to know that you throw in a lot of data and a lot of observations, and then you build decision trees, and you build a lot of decision trees, like we just had an example of from the other group, and then you cluster these decision trees into forests that belongs together, using fancy mathematics like this Gini formula, which is really cool. and then these clusters of decision trees or then random forests are quite useful. So whenever you then get a new observation, a new object in, you know kind of which cluster it belongs to, and then you can find out what path that object or observation will take when it enters this nice forest. That is the conceptual explanation, which you can shoot down afterwards. And then the layman's so the 8-year-old explanation here would be, you know, if you 8-year-old Sundara, your little brother who goes to the kindergarten, if you throw in all the kids in his kindergarten into the kindergarten, and then some will go to the kitchen because they're hungry, and some will go to the toy room because they want to play, and some will go to the bathroom because they need to go to the bathroom. And and if you go to the toy room, some will choose the ball, and some will choose the card game. And the ones that choose the ball, some will go and play to the field to the left, and some will play to the field to the right. And if you throw this enough times, and you watch all the kids during a year, during 2 years, you will start developing patterns. And then after a couple of years, you can fairly easily predict that if you are a boy that is really hungry, he will go to the kitchen, he will turn to the refrigerator, he will open it, and he will drink a glass of milk, for instance.
I think you covered it pretty good. This is what we have understood in general, that it's based on neural networks, which is basically how we think. So you have to think of this both in terms of data going in also. So when you're a 10-year-old or an 8-year-old kid and you see a toy, you may initially not associate it with a toy room. You may associate with the kitchen. So the whole concept of a random forest is that, as decision trees get more complex, you need a simpler way to simplify it, optimize it. And that is done by making the right choice as to whether the ball goes to the kitchen or it goes to the toy room. And that's the algorithm which kind of makes it much more effective. So I think that's pretty much everything like that.
Any questions?
So why do you need to cluster a tree into forests?
The idea is to kind of try to reduce the amount of diversity that you're seeing in the actual data that you're processing. So if you see a bunch.
Diversity or increase it?
Sorry.
So if you have one tree, right, it's just one set of observations, right? So I'm cheating because I'm an scientist. When you have a tree, it's one set of observations based on, in their example, one eyewitness, right? So in your case, you have forest, it would be as if you had 1,000 eyewitnesses. So why might 1,000 eyewitnesses be better than one eyewitness in, let's say, crime?
We haven't really approached it from the observation point of view, more from data storage point of view. So if you take the case of a toy, you would say that you're more likely to find a toy in a toy room. So you make that as a part of a forest and things that are in there. So it's a kind of sub-classification of that.
But isn't that because maybe you've never seen the toy before?
Yeah, when you've never seen it before, then you're basically making an estimate or a guess as to where it should belong. And hopefully with time you get better at making that guess.
Yes, it's, this is also used for voice and video and image classification, right? So if you get thrown something at you that is a rabbit, but it looks completely a little bit different from a rabbit, then it's useful to use the sort of rabbit decision the forest of the rabbit decision trees to classify it rather than sort of step into the.
So in the crime example is probably really helpful. So if one person observed a crime, how likely do you think they are to be wrong about a detail than 1,000 people agreeing, right? So by ensembling and putting together, so mathematically speaking, the reason a tree is so simple is because it's very computationally math intensive. But because it's so simple and not a really complicated algorithm, the likelihood for error is pretty high. So clustering or ensembling, right, making it into a forest is a really smart move because each tree has high error, but it has error with different things. So for example, if everyone in this room observed the crime, let's say 5% of people said that the person had glasses and 95% of people said they
actually gotten the correct answer, even though 5% of people were wrong. So that's just trying to point like that's one of the keys to moving from trees to forests. That's why you do it, because in aggregate you tend to reduce your error significantly. So just wanted to point that out because that's a very important part of decision trees and why we do trees and ensembling and not just a forest.
Any other questions?
So are you saying that every tree votes for the answer, and the majority wins then?
Pretty much.
Okay.
Yep, and that's so what you just explained is called ensembling. So you can do ensembling actually at an even bigger level, where let's say you use, people are going to talk about other algorithms, right? Let's say you need to classify things into categories, right? Boy or girl, and you can use 15 different classification methods, right? So so in each can be wrong in its own way, right? That's why it's called a model. It's not perfect. It's an approximation, right? Each model can be different in a wrong way. So if you were to run, let's say, 5 different models and take a vote, like you said, then you are more likely to have a right answer, and that's called ensembling. And what you just explained is exactly it. That's literally what happens.
For small data sets, because probably for bigger data sets it becomes redundant at that point?
No, because the error is in the model, not in the data.
So it's not really an optimization of decision trees. It's actually an improvement on the results.
Reduction of the error.
Okay. We probably missed that one nice and neat.
15 minutes. We spent an entire day teaching this, so you guys at 15 minutes is fair. Any other questions? Thank you very much.
Thank you.
Ja, det er det. Ja. Det er eksemplene har vært stemmer og surr. Det var en bra eksempel. Ja. En bra bilde, liksom. Ja. Det bildet der var at alle trærne stemmer. Ja. Den demokratisk på den. Det stod at det ikke korrelerte, så det gjør det.
Well, I suppose it's going to be me.
Yeah.
So recurrent neural networks, let's decompose the terms. Then, well, neural networks, pretty much convenient to say, are networks or neurons, and is basically a way for us to represent a brain. Neurons, as you know, are cells that fire other cells with signals, electricity, and in the same sense, we represent those neurons with nodes in a diagram. To say something of the machine learning algorithm. So neural networks just represents the brain, and we have a set input data set, and then we expect a certain output out of the so that's pretty much basic about the neural networks. And then recurrent neural networks, what happens is that the layers in the neurons are allowed to trigger themselves or other neurons in the same layer. So what this does is that it creates a state, or it just basically creates a memory of what happened in the previous input. This is definitely useful for what it is known as recognition, and what I understand of recognition is basically classification and prediction combined. So you will predict what is going to happen, and you will classify immediately, so you recognize it. That example will be for voice recognition or handwritten recognition, when there is continuous data and you want to know what happens after from the previous. So if, for example, you want to evaluate the likelihood of the next letter in the voice, or the next letter in the handwritten pattern. So why? Because you know how probable is that the next letter is an A if the previous is a B and the previous of that is a C. So you will recognize what is going to happen. That's pretty much the 8 years old explanation when you want to recognize the next thing that's going to happen from what happened before. Any questions?
Do you guys have another real world example that you can share?
You guys remember?
So if you, or one of the most interesting I read about is that you can, if you have a lot of natural speech like poems of Shakespeare, you just gather all that data together and feed it into the recurring neural network. And after some training, it seems that it actually can generate a poem by Shakespeare, or appears to be a poem by Shakespeare. And if we have sufficiently enough data in, it would be hard for us to recognize what is actually a poem written by Shakespeare and was something generated by the computer. And of course it is really interesting when you, journalists, if you have a sports report, perhaps it is boring, so you have a lot of data from previous sports reports. Perhaps you don't have to even write the new report, you just feed in the old data and some details, and you get out something that appears to be written by a journalist.
And I think the most important word that we discovered in this machine learning model is the word memory, and the idea that if we think about neurons, they will fire the adjacent neuron with electricity. But if they are going to be fed by the same output that they had before, they will remember, they will know, they will be more likely to fire, and therefore it will happen more consistently. So if you mention a word and then there is another word that goes in the same sentence as Shakespeare will do, then the next set of that data will be easy to recognize that that's Shakespeare, because it remembers that previous data set had that input.
Any other questions? No? Okay, thank you guys.
Juksa du? Jeg tenkte på deg som en stiv i hoften
Okay, so we're going to try to explain the LSTM, or the long short-term memory algorithm, which is an implementation of a recurrent neural network. The LSTM tries to solve one of the issues that recurrent neural networks has, in that when you have errors, it's biased towards fixing the end of the chain. So in recurrent neural networks, you use in a normal neural network, you would have an input and try to predict some output. So, for example, if I said ice, maybe you would say cold, or maybe you would say water, or whatever the network is trying to do. But in a recurrent neural network, we would also use that as, you could either use the output or some variant or transformation of the output as the input to the next state of the function. So, for example, when you have ice and cream, then is maybe, or yeah, if you have ice here and is here, you would expect another output than if you had ice and cream. The bias in recurrent neural networks is to change a lot at this part of the algorithm and not as much at the end, at the start of the algorithm. So LSTM is mainly a way to try to distribute the learning throughout. It does that through maths.
Was there another example that you guys found that you can share?
We did also have heard about an example with music. So I guess it's the same as the poetry example, that you just push a lot of music into the algorithm and it would produce something that could be said to be similar to initial generated, non-generated songs.
Stock prediction, anything related to time series in general.
Any questions?
Yeah, on the recurrent neural network, you have the loop on the same layer. Is the difference here that you can loop a layer before?
Basically, it's the same layer again. You will have the same layer over and over, right? So it's instead of grow vertical, it's grow horizontally, right? So the difference is, try to explain is that in the old classic model, it starts to forget the early stages, right? And LSTM, what it does is helping to remember, so it doesn't end up with Alzheimer's like this old one.
Yeah, okay, I understood a little bit differently, but
probably.
Yeah, because I thought that this entire stuff in the middle was the neural network, and then so this entire thing is a neural network. So you don't really have different neural networks; you just have the same network, and then
in different states.
Yeah, in different states.
It feeds its old state into the new iteration.
Yeah. So this isn't really a layer of a neural network, it's just an entire neural network. So yeah, we can go into the details of the neural network. Because of time constraints.
Any other questions? Yeah?
Just to connect the dots. What is then the connection in your mind between the decision trees and in forests and the neural network and LSTM?
Very little.
Very little?
Well,
you wouldn't say that the recurrent neural network are kind of consists of simple decision trees in a network?
No, I don't think I would say that. I think they have different algorithms, different foundational algorithms.
Yeah, I think they are made for different types of problems, maybe. Like one is better for classification and the other is better for generation or prediction. Yeah, but a hard question.
Any other questions? Okay, thank you guys. Number 5, almost done for the evening.
Skal stå der og se. Lykke til.
Okay, we tried to learn about deep belief networks, and it was really hard. No one had heard about it or worked with things before. So we'll try to render what we think we have understood. And if someone knows better, they should probably correct me. So it's a deep learning algorithm which has some layers, as they usually do. What's special with this algorithm is that except for the first two layers, so I guess this is the learning inputs or something, and here there's some bidirectional kind of connection between this and some variables in this layer. Yeah, and in between these ones, for each layer, you learn just this way. So you learn something in this layer, and you use the, I guess, inferred variables from this layer to train the next. So for example, if you have, I guess, a picture, and you have the border, as we talked about earlier, you can, for example, say something about that here and something else. For example, is there a cat? I don't know. And each of these can be seen as a restricted Boltzmann machine. And yeah, I'm not sure if a 10-year-old would understand that. I'll probably skip that, just so it gets a bit easier. And at some point here, you end up with an output.
I can give it some input, maybe.
Yeah.
Yeah, like, this is probably very, this is actually a neural network kind of. The difference is that this word here was what we were really struggling to understand.
Yeah.
What is actually the belief? And what we, the theory we had was that the difference between the layers is that this is going in one direction, but this is actually going in two directions. And so what it's doing is taking a lot of input, and then it actually recreates the input, like a new set of input that is probabilistically. It's like it takes maybe thousands of inputs, and then it does some kind of a belief. It creates a belief system, which is actually a subset, or like a small new set, which is not as many as the beginning input set. So that it actually is easier to have many layers, because you have fewer points per layer.
It's like the dimension reduction.
Yes, exactly.
So for each layer, you can say something about the correlation between the past set and I guess the new one, since you train a new probabilistic model for each layer.
Yes. So from here, I think it's like a normal neural network.
No, this is the
well,
part.
isn't it?
So this is linear. So that's why it's called belief, I think.
Yes, but I think it's the first part that's the belief, isn't it?
We believe you.
I'm not sure either, but
and this can be used
classification and stuff like this. Yeah.
Reconstructing the books.
Yeah.
Yes. Could you please help us here?
So I am not going to give you the answers. The goal is for you to work with the group, right? So did anyone else have a specific understanding that was not covered yet? No? Okay. Any other questions from the class?
Those deep mean that you got like
many layers. Yes.
And belief is probably because you're using less data, so you are kind of approximating, and you think that you're gonna get to the same point.
I think the belief is due to that you're creating a probabilistic set of input, and that's your belief. You're believing in something that it's probable that you can actually represent the whole input state in a lesser input state, like with lesser input. And so you reduce, as he says, you reduce the amount of calculation. Yes, that's kind of what I think.
What happens between the layers?
Where there are some weights, which I guess is the you use to calibrate your method. So it's some kind of matrix. I guess you just multiply it by the output of the last layer, and that's your calibration. And in each layer, it kind of learns. So that's a learning process in each layer to like infer the next layer. So it's kind of like the correlation matrix, I guess, you end up with some kind of a reduced set that represents some kind of connection in the past set.
Yes, and usually the futures of each layer is a more and more abstract thing. It's like it starts with eyes, like shapes, and then it takes the shapes and put them together to bigger and bigger, more abstract objects for each layer. So at the end, it actually understands it's a car, but in the start, it just takes a lot of angles to make an eye or something, and then it creates an elephant or whatever.
Any other questions? No? Okay, thank you guys very much.
So we have K nearest neighbor and its classification. And you can see my beautiful drawing here. You have dog lovers and cat lovers because that's what 10-year-olds care about. And we want to know what this guy likes. And we're trying to figure out which K is the best. I'm going to explain the K, which is if we consider his 3 nearest neighbors, it's the 3NN, not the KNN. We set K to 3 and we count his neighbors. And we see that, okay, he has 2 cat lovers and 1 dog lover neighbor. So this must be a cat lover. We have the solution for this, and we can say that that was wrong. So you get an error like we discussed, was mentioned earlier. We want to minimize this error. So we try again with K5, which is the larger circle. You have 5 neighbors here. You can see that he has 3 dog lover neighbors and 2 cat lovers. They vote for the majority is dog, so we guess that this is a dog lover. And we keep repeating this for every point in the entire data set. And we switch out, we test with different Ks. We test with K1, K2, the entire spectrum, and we figure out the K which best suits the model. And that's during the training. So let's say we figure out that K5 is best for this model. So then we drop, let's say we drop in a new guy who's up here. We count in the prediction phase, we get a new data, drop it into the n-dimensional whatever, and you count the neighbors, and the majority wins. The majority thing is a simplification, because you get a real shitty model just by counting the neighbors. So you can use distance, or you can use weights to give the neighbors difference. Yeah, so you sum up and do maths, and the entire trick with this model is actually figuring out how to weight the neighbors. Yeah.
Good. So the basic idea is that you are what you resemble, and then the applications that we found is basically predicting economic events, which is stock market prices. But we also found a case where they used this algorithm to study financial distress, or predicting financial distress in Iran. So after the global financial crisis, they were very interested in the likelihood of bankruptcy, and this is the first stage of bankruptcy. The second application that we found was in computer vision, face recognition. Most of you are probably familiar with that, and also to recognize handwriting. And if the content is a video, you can also recognize sign language. Yes, so that's the different ones you can use. Any questions? Don't ask me.
Okay, thank you guys very much. our talks for this evening. Obviously, we want you guys to all come back tomorrow. And we are also going to be hosting another session in June, which is going to be a longer session. And we're going to bring in some more speakers as well from the Bay Area and maybe even some other locations that specialize in different areas of artificial intelligence and research. And we'll show a lot more of real-world applications and how this could be used in areas such as like agriculture or law, fintech. So there are many, many different applications of artificial intelligence as you've gotten some experience now and can understand how these algorithms can be applied. So that would be it for this evening. I hope you guys have a good night, and we'll see you tomorrow.
Det var ålreit.